Algebra 2, 6.4, use inverse functions. An inverse relation interchanges the input and output values of the original relation. This means that the domain and range are also interchanged. So basically our input, which is usually x, and our output, which is usually y, are going to switch. So for an original function of 0, 6, 1, 4, 2, 2, 3, 0, and 4, negative 2, our inverse relation is going to switch all of those. So our y becomes our x, so 6, and our x becomes our y, so 0. And we keep going. So 4, 1, 2, 2, 0, 3, and negative 2, 4. The graph of an inverse relation is a reflection over y equals x of the graph of the original relation. So, to find the inverse of a relation given by an equation in x and y, first you switch x and y, and then you solve for y. So, if we want to find the inverse of the equation y equals 3x minus 5, we start by step 1, switching our x and y. So, x equals 3y minus 5. And now we solve for y. So I'm going to add 5. So I get x plus 5 equals 3y. Divide by 3. So I get y equals x plus 5 over 3. So that is the inverse of 3x minus 5. Okay. Now for a slightly trickier definition. Inverse functions. Functions f and g are inverses of each other, provided f of g of x equals x, and g of f of x equals x. The function g is denoted by f to the negative 1, which is read as f inverse. So we want to verify that 3x minus 5 and 1/3 x plus 5/3 are inverse functions. So to verify, anytime it says verify, we have two steps. Step 1, show that f of g of x simplifies down to x. And step 2 is show that g of f of x simplifies down to x. So I'm going to plug g in for the x in f. So 3 times 1/3 x plus 5/3 minus 5. So I'm going to distribute. I get 3/3 x plus 15/3 minus 5. 3/3 simplifies to 1, so I just have x. 15/3 simplifies to 5, so x plus 5 minus 5. These two cancel, so I am left with just x. So I showed, all of this is my showing, I have to show my work, that f of g of x is equal to x. Now I have to show that g of f of x is equal to x. So I'm going to plug f into x over here in g. So 1/3 times 3x minus 5 plus 5/3. I distribute my 1/3. So 1/3 times 3 is 3/3. 1/3 times 5 is 5/3, so 3/3 x minus 5/3 plus 5/3. These cancel. 3 over 3 simplifies to 1, so I get x. So I've shown this way, and I've shown this way. So I've proven this form, or this definition, which is f of g of x is equal to x, and g of f of x is equal to x. So, example 3. Elastic bands can be used in exercising to provide a range of resistance. A band's resistance in pounds can be modeled by R equals 3/8 L minus 5, where L is the total length of the stretched band in inches. Find the inverse of the model. So, first thing I'm going to do is switch my variables to x and y. So y equals 3/8 x minus 5. Now I'm going to switch my x and y where they are in my equation. So x equals 3/8 y minus 5. Now I solve for y. So I add 5, so I get x plus 5 equals 3/8 y. And then I multiply by my reciprocal, which is 8/3 on both sides, to get these to cancel. So I get y equals 8/3 x plus 5. And now I have to put my original variables back in. So, in this one, my R was by itself. So in this one, my L is going to be by itself. So now we use the inverse function to find the length at which the band provides 19 pounds of resistance. So I'm going to plug in 19 for R. So L equals 8/3 times 19 plus 5. So 19 plus 5 is 24. 8/3, so if I divide by 3 first, 24 divided by 3 is 8. So I get 8 times 8, which is 64. And total length is in inches. So 64 inches. So, now, the graphs of the power functions f of x equals x squared and g of x equals x to the third are shown below along with their reflections in the line y equals x. Remember that their reflections in the line y equals x means that it is their inverses. Okay? So, the inverse of x squared, so here's the original x squared curve, and here is the inverse of x squared. Now we're going to perform the vertical line test to figure out if this dotted line here is a function. So I look, and pretty much anywhere I draw the line, I'm going to hit it more than once. So it is not a function. Over here, we have x to the third, and then we have the inverse of x to the third. And pretty much anywhere I draw a line here, in fact, everywhere I draw a line over there, it'll only hit once. So this is a function. Okay, the horizontal line test. The inverse of a function f is also a function if and only if no horizontal line intersects the graph of f more than once. So if we look at just our original graph here, which is the solid one, it passes the vertical line test, so it is a function. And then the horizontal line test, it does not pass, which means that the inverse is not a function, which we could tell if we graphed the inverse, but we don't necessarily always want to graph the inverse. So this is a shortcut. Okay, then x to the third passes the vertical line test, and it also, we're looking at the solid line again, passes the horizontal line test. So that means that it is a function, which we already knew because we graphed the inverse of the function, but we don't necessarily always want to. So if f does not pass the horizontal line test, then you must restrict the domain to allow it to pass the horizontal line test. So if I want to talk about an inverse function of this function, I'm going to have to restrict my domain and say, let's just look at the positive numbers, because then just this line here passes the horizontal line test. We're basically ignoring this side. So this part passes the horizontal line test, but the whole thing doesn't. So we had to restrict our domain. So now, for example 4, we are going to find the inverse of f, where f is x squared. X is greater than 0, so they restricted our domain. And then we're going to graph f and f inverse. So, I'm going to rewrite this as y equals x squared. Okay, I'm going to switch my x and y, so x equals y squared. To get the y by itself, I have to undo this squared, which I do by taking the square root. So I get y equals the square root of x. Now, since this says x is greater than 0, that means that it's the positive square root. If it was x is less than 0, then it would be the negative square root. So, I'm going to graph, so I'm going to do f of x. So here's x. I'm going to do f of x and then f inverse of x. So if x is 0, then 0 squared is 0. So I'm going to graph 0, 0. If x is 1, 1 squared is 1. So I'm going to go to 1, 1. If x is 2, then x squared, 2 squared is 4. So I'm going to go to 2, 4 and put a dot. If x is 3, 3 squared is 9. So I go to 3, 9. So that right there is f of x. Okay, now f inverse of x. The square root of 0 is 0. So 0, 0 is also on that graph. The square root of 1 is 1, so 1, 1 is also on that graph. The square root of 2 isn't a pretty number, neither is the square root of 3. So let's go to 4. The square root of 4 is 2. So I'm going to go to 4, 2, and put a dot. And then the next number that comes out pretty is 9. The square root of 9 is 3. So I'm going to go to 9, 3. And then I'm going to connect my points just like that. So this is f inverse of x. So if we draw that line, which is the y equals x line, it would be there. And if we look at this, this is a reflection over this line and vice versa. So if you look at it like it's a mirror, they are the same on either side of the line. So it is symmetrical, so it is a reflection. Oh, for example 5, we are going to determine whether the inverse of f is a function. Then we are going to find the inverse. So, step 1. Graph f of x equals 2x to the third plus 1 on your calculator. So, we are going to get out our calculator. We're going to turn it on. Then we're going to hit the y equals button. Then we're going to type 2x to the third plus 1 into our calculator and graph. Okay, so here's our graph. Does the graph pass the horizontal line test? So anywhere I draw a horizontal line, it will only hit my graph once. Here, let's change my window so that it's easier to see. 6. So there we go. That's an easier line to see. So does it pass the horizontal line test? Anywhere I draw a horizontal line, it will only intersect once. It's a little tricky to see here in the middle, but it's true, it will only intersect it once. So, yes, it does pass the horizontal line test. Is the inverse a function? Well, if it passes the horizontal line test, then yes, the inverse is a function. So, now we are going to put our calculator away and rewrite the equation with x and y. So instead of f of x, I'm going to say y equals 2x to the third plus 1. Now I'm going to switch my x and y. So x equals 2y to the third plus 1. Now I'm going to solve for y. So I subtract 1. So I get 2y to the third equals x minus 1. Divide by 2. Y to the third equals x minus 1 over 2. Now, to get rid of this cubed, I have to take the third root, or the cube root. Okay, so this cancels, and I get y equals the cubed root of x minus 1 over 2. So that is my inverse. Example 6. The average price, P, in dollars for a National Football League ticket can be modeled by P equals 35T to the 0.192 power, where T is the number of years since 1995. Find the inverse model that gives time as a function of the average ticket price. So I'm going to rewrite this using x and y. So y equals 35x to the 0.192 power. Now I'm going to switch my x and y. So x equals 35y to the 0.192 power. Now I'm going to solve for y. So first thing I do is divide by 35. These cancel. So I get x over 35 equals y to the 0.192. Now, to get rid of this, I can't really take the 0.192 root of something. So, what I'm going to do is I'm going to raise everything to the 1 over 0.192 power. The reason I do this is so that when I raise a power to a power, I multiply. I have 0.192 in the numerator, and I have 0.192 in the denominator, so they cancel, and I get y equals x over 35 to the 1 over 0.192 power. Okay? Oop, one more step. Now I have to change it back into p and t. Up here, p was by itself. So now t is going to be by itself. So t equals p over 35 to the 1 over 0.192 power. So that is our final answer.